Hi there everyone, it's Mr. Pope from Wilmington Grammar School for Boys, and today we're going to be looking at some radians, some basic radian applications. So first of all, what is a radian? Well, a radian is a unit of measure of angles, and up to this point you should be familiar with angles being represented in degrees, i.e. 90 degrees, 180 degrees, 360 degrees in a full turn, and so on. Now, what I want you guys to get into your heads, ideally, is that if I draw a sector, like so, where it has a radius r, but also the length of the arc is also r, then this is defined to be 1 radian. Okay, and you're probably thinking, well, hold on a minute, how is that helpful? Surely you'd want it in smaller subdivisions. And the reason for that is because, well, if I take a straight line, then instead of seeing this angle here as 180 degrees, we're now going to see it as pi radians. It has been rotated pi. We've talked about radians before, and essentially they're just better units to work with. Things need to work out a lot more. For example, degrees, the units are in degrees, whereas pi, with radians, they're degreeless, or rather they're dimensionless. They're just quantities, and it makes sense from a more intuitive point of view to define an angle with respect to a circle or a sector of a circle where this quantity just doesn't change. Doesn't matter what the value of r is, you can scale this thing up, you can scale it down. That's always going to be 1 radian. Doesn't matter if I rotate it, enlarge it, shrink it, that is always going to be 1 radian. The upshot of this is quite a lot of formulas that you would have known at GCSE are going to simplify down. For example, if I look at the area, let's go over here. Let's say I look at the area of a sector, so area of a sector, then at GCSE you would have known that's the area of a whole circle, which is pi r squared, and then multiplied by the angle theta over the angles, the total angles of a circle. It's literally the fraction of the circle, and usually we'd leave that as over 360 degrees. But now look what happens if instead of out of 360 degrees it's now out of, and we're working in radians, a whole circle would be 2 pi. Okay, if 180 degrees is pi, then 2 lots of 180 degrees is 2 pi, right? A whole circle would be 2 pi. Now what happens? The pi's cancel, and you're just left with r squared times theta all over 2, or just half of that. So actually, when working with radians, areas of sectors become incredibly easy to work out. It's just half of the radius squared times by the angle in radians. And then if I look at arc length, an even easier cancellation happens, because arc length is just the circumference of a circle, 2 pi r, times by the fraction of that circle, because the arc is part of the circle, so of the circumference, sorry. So for this is my circle, then my sector would be, this is a sector, and the arc is this bit here. It's the length of the perimeter for every theta and r of the circle, where it's r is the radius from the centre. And so we've got a similar thing here. This is going to be over 2 pi. The 2 pi's cancel, and we're just left with r times theta. Now this is amazing. All you need to do to find the arc length is just r times the theta. It's amazing. And that should make sense on the original definition, because when theta is 1, then r times 1 is r, which means you've just got 1 r on the curved bit going around. So it's consistent. Okay, now how do you deal with stuff in radians? Well, what you need to do is, for most calculators, the Casio ones, you need to press Shift and then the menu button, which should now be set up. And then it will ask for angle, and then degrees, DEG, or radians, rads, and usually there's gradients or gra. It's essentially that's a weird thing that only engineers use. I think it's got something to do with percentages. It's dumb. I mean you can use it. It's okay, but radians is found there. You can tell which mode your calculator's in, because for most calculators there'll be a little black square with maybe an R or a D in it at the top, and that's always a good indicator of what kind of angles we're working with. A recap from GCSE, there's other geometric properties we should be aware of. Not necessarily to do with radians, but just helping with us with our geometric shapes. So for example, the big one is if I have a triangle where this is an angle theta and this is a length A and this is length B, then the area of this triangle is just 1/2 of A times B times by sine of that angle theta. This is also often the theta is replaced with C, so most people would say half AB sine C. It doesn't matter particularly. Being able to find the area of a triangle using that is enough. I mean, to do with trigonometry, those are the main ones. There's other trigonometric rules with triangles. For example, if I have a general triangle looking like this, where the sides are capital A, capital B, capital C, and the opposite angles are little a, little b, and little c, then for the sine rule from GCSE, the reciprocal of this is also true, but capital A over sine of little a is the same as capital B over sine of little b is the same as capital C of sine of little c, like so. The reciprocal of this is true, so if you want the sines on the top, that's perfectly valid. And for the cosine rule of any triangle, then a squared equals b squared plus c squared. It's like Pythagoras, and then you minus 2 lots of bc sine of the opposite angle A, like so. Generally speak, you're not going to be given these formula, so you need to have them memorized by now. When you're doing A-level maths and beyond. To be honest, it's like the quadratic formula. You do it a couple of thousand times, it's just ingrained. And generally speaking, whenever you're solving problems to do with circles or triangles, stuff like that, having a good idea of trig, radians, angles, that kind of thing, is a good thing to have. So I'd commit this kind of stuff to memory. Small angle approximations. Right, now we are going to be talking about Taylor series and expansions and how all real functions, real analytic functions can be approximated with an appropriate series. We are going to deal with that, but the upshot is that when theta is really small, and the way we're going to denote that is when theta tends to 0, then the following identities happen, i.e., and to be fair, this only works when theta is in radians. Okay, and the reason for that is because the Taylor expansions and for complex functions, the Laurent expansions don't work unless it's in radians. So sine theta will tend to theta. Cosine theta will tend to 1 minus theta squared over 2, rather cryptically, and tan of theta will tend to theta as well. Okay, so yeah, just be aware, these are things that are given to you in the formula booklet. You don't need to memorize them, but you just do need to be aware that when theta tends to 0, you can approximate some trig functions as some nice polynomial ones, and that does tend to make things a little bit easier, especially if the question prompts you to do things geometric, to approximate values for small theta. Now, optimization problems. Now, I've got some examples of this, but essentially, when you're dealing with radians, you're probably going to be dealing with funny boxes of different shapes, or you want to maximize or minimize things. And just as a recap, generally speaking, if I want to minimize, let's say, P for a change in, I don't know, Q, then that means that if I find the quantity dP by dQ and set it equal to 0, I will find for a given Q value a minimum or maximum P value. And that's really important. It happens a lot with radian stuff when you I don't know, let's say, an example, let's say I've got a wedge like so, and I've got this angle here, let's say that's theta, and I don't know, let's say I've got this R value, I've got a constant radius of say 6, and I've got a height like this, and then let's suppose I have a constant volume of say 200 pi units cubed. Then can I find a maximum surface area? Okay, so if I wanted to find a max area of this shape, well, let's deal with that, see where it goes. So what is the volume of this shape? Well, it's going to be the area of the sector, because this is a prism. If I was to drop this down, this is like a wedge of cheese. Then it's the area of the sector, which is a half r squared theta, and then it's times by the height h. Now I know the volume is 200 pi. Half r squared is 6 squared, which is 36. Theta, I don't know what it is, and the height, I don't know what it is. So I've got 200 pi equals half of 36, which is 18, times by theta times by h. So actually, theta times by h is 200 pi over 18. And that simplifies down to 100 over 9. I thought it would go a bit more than that, never mind. And so, let's say I want to find the maximum area for a theta. So for what theta gives a maximum area? Okay, so if I look at the surface area of this whole thing, well, how many sections are there? Well, there's the base, which is the same as the top bit because they're both sectors. So let's do that bit first. So the pink bits are going to be two lots of half r squared theta. So half 6 squared times by theta. So the 2 and the half cancel, so this is going to be 36 theta. If I was to look at the curved bit on the outside, which is going to be this bit, then well, that is going to be the arc length, which is r theta, times by the height, because that's like a rectangle laid flat, so that's h. And now, if you think about it, I can divide by theta both sides, in this original thing here, to get h is 100 pi over 9 theta. So actually, this thing is just going to become r theta times by 100 pi over 9 theta. Oh, I know what r is, you silly boy. R is 6. So this is actually going to be 600 pi over 9. the thetas cancel, so this is going to be 600 pi over 9. I can divide by 3 top and bottom to get 200 pi over 3. So that's interesting. That's a constant. Cool. So adverse effect, that bit there is always a constant area. Doesn't matter what we change theta to. Interesting. So we'll take that and put it over here. And then the final areas to consider are the rectangular side bit. So that side bit and the side bit to the left-hand side. So what are they going to be? Well, they're just going to be 6 times by h, and there's 2 of them. So I believe that's 12h, and that's 12 lots of h, which is 100 pi over 9 theta. The 12 and the 9 can cancel, so that's a 3 and that's a 4. So it's actually 400 pi over 3 theta. So when you add all these things together, the total surface area is the green bits, which is 400 pi over 3 theta to the minus 1. The orange bit is 200 pi over 3, plus the pink bit is 36 theta. And now if I want to find the maximum S for a given theta, where S is the surface area, then I need to find ds by d theta and set that equal to 0. So remember the power rule, bring the power to the front, so that's minus 400 pi cubed, and then theta, drop a power, minus 2. This is a constant, so it disappears, and 36 theta plus 36, like so. I now set this equal to 0 and solve. So if I add that tome over, I'm going to get 36 equals 400 pi over 3, lots of 1 over theta squared, which is theta to the minus 2. If I times by 3, 336 is 108, and this is over 400 pi. This equals 1 over theta squared. So then if I flip this, so it's theta, and then this is 400 pi over 108, and then square root this. I want the positive theta to have another negative angle, just doesn't make sense. So the square root of fraction 400 shift pi over 108, that will mean theta has to be approximately 3.411 radians for this to be maximal, which is interesting. That's more interesting. That's more than pi, so it's more than 180 degrees. Have I done this right? Minus 1, yeah. Okay, so next up, will this give a maximal S? Well, we can check that by finding the second derivative, ds by d theta squared, and then minus 2 will come down, so it'll become 800 pi over 3 theta to the minus 3. 36 disappears to nothing, and clearly if I substitute a positive value in here, which is 3.411, this will mean the second derivative is positive. Ooh. Is that right? No, it can't be right, because then that means it's a minimum. Where have I made a mistake? Oh, interesting. So it looks like this will actually give a minimal surface area. Just out of curiosity, when theta is that, what's going on over here for h? Well, there will be 100 pi over 9 times by 1 over theta, which is going to be the square root of 108 over 400 pi. And that answer, so fraction 100 shift pi over 9, and then divide that by the answer. apparently the h is 10.23. So actually, there isn't a maximal area to this, there's a minimum area. So the minimum area to all this is when h is 10.23, theta is 3.11, and if I take that surface area and plug it in, then hold on, shift square root of fraction 400 shift pi over 108, and then I'm going to plug that into the s value at the top, so fraction 400 shift pi over 3, lots of answer, plus 200 pi over 3, plus 36 times the answer 455 is the minimal surface area for a volume of 200 pi units cubed. Yeah, interesting. So there you go. So it actually has a minimal area of 455.03 units squared for when theta is 3.411 radians and the height is 10.23. And the idea is if you, I've proven it's a minimum because the second derivative is positive. That means it's going from a negative. If I was to plot the s function against theta, that means for theta values, it's going from a negative gradient to a minimum to up positive, because the gradient of ds d theta is constantly increasing. 455.03 is the minimum. So yeah, interesting problems. Hopefully I'll show another one in a second. But yeah, let's crack on with some examples. So, okay, first question. If you want to pause it, give it a go yourself, see if you can figure it out. Okay, change to red pen. Figure 1 shows a sector AOB of a circle with centre O, radius 5 and angle AOB 40 degrees. The attempt of a student to find the area of the sector is shown below. So the area of the sector is half r squared theta. So they're saying it's a half of 5 squared times 40, so it's 500. Explain the error made by the student. Right, this formula only works for radians, not degrees. So you can't just do that. Write out a correct solution. Well, we could have turned 40 degrees into radians. Well, 40 degrees out of, let's say, 360 degrees is the same as what angle in radians out of a total of 2 pi? Well, 40 out of 360 cancels down to 1/9. So theta over 2 pi must be 1/9. So that means theta equals 2 pi over 9 as radians. So the area of the sector would be a half r squared times theta, where it's a half of the radius squared, which is 5 squared, times by theta, which is now 2 pi over 9. So the correct answer is that 2 and that 2 will cancel. 5 squared is 25, so it's 25 pi over 9 centimetres squared. And if you want that as a decimal, 25 shift pi over 9. We're looking at approximately 8.73 centimetres squared. Why does this make more sense? Well, look, if this side is 5, even if I was to draw a 5 by 5 square like that, I know this sector, well, that's 40 degrees, so it's not going to be halfway, but I know this sector has to be less than 25 centimetres squared. So this answer of 500 centimetres squared is ridiculous. So that's obviously wrong. Whereas 8.73, it's about just over a third of 25 centimetres cubed. That seems legit. That sector probably is about a third of that square. So yeah, that seems pretty likely to me. Okay, so next one, small angles. Pause the video, give it a go yourself. Okay, given that theta is small and measured in radians, use the small angle approximations to find the approximate value of that. Right, now if cosine theta is 1 minus theta squared over 2, when theta tends to 0, then cosine of now the input is 4 theta. This is going to tend to 1 minus 4 theta squared over 2, which is the same as 1 minus 16 theta squared over 2, which is going to be 8 theta squared. Next up, if sine theta tends to theta, for this is all for when theta tends to 0, by the way, then sine of 3 theta, which is what we've got over here, is going to tend to 3 theta. So let's just crack on and see what happens there. So on the top, we have 1 minus cosine 4 theta. So we're going to have 1 minus cosine 4 theta, which is 1 minus 8 theta squared. On the bottom, I've got 2 theta times by sine 3 theta, which is a 3 theta there, times. So let's distribute this. 1 minus the 1 will cancel, and minus 8 theta squared is going to be 8 theta squared. All over 2 theta times 3 theta is 6 theta squared. The theta squareds cancel. 8 over 6 is 4/3. So when theta is really, really small, this identity approximates to 4/3. Okay, the reason we do this kind of stuff is when theta is really, really small, look what happens. Cosine of 0 is 1, so we've got a 1 minus a 1 on the top, which is 0, over 2 lots of 0 is 0, and sine of 3 lots of 0 is sine of 0, which is 0. So when we have a 0 over 0 thing, we're left scratching our heads because we can't do 0 divided by 0. We have to use some other kind of alternate way of solving this. And one way of doing that is by considering the Taylor series, and another way is just using small angle approximations. And in this case, 4/3 is the way forward. Later on, I'll teach you other things like L'Hopital's rule of convergence, all that kind of stuff. But small angle approximations are really good for when the quotient heavily relies on trig. Okay, right, here you go, some geometric stuff. So, pause the video, give it a go yourself. Okay, figure 1 is a sketch representing the cross-section of a large tent A, B, C, D, E, F. A, B and D, E are line segments of equal length. Okay, so immediately that side is the same as that side. Cool. FAB, angle FAB and DEF are equal. Okay, so this angle and this angle are the same. F is the midpoint of the straight line AE and FC. Hold on, F is the midpoint of AE, right? So that side is the same as this one. Okay, so it looks like they're congruent triangles because I've got side angles side here, side angle side. So essentially they're the same triangles, they're congruent. Cool. And AE and FC are perpendicular to A. Hold on. Oh, and FC is perpendicular. Okay, so that means if I draw a straight line from F to C, what that's just saying is C is at the very top of this, and that's 90 degrees. Okay, BCD is an arc of a circle of radius 3.5 meters with center at F. Okay, so that's 3.5 meters. Okay, it is given that AF to FE is 3.7. Right, so that's 3.7. This is 3.7. BF to FD is 3.5, and that's 3. Well, that's clearly 3.5 because they're radii of circles. And BFD is 1.77 radians. Ah, so this is 1.77 radians. Okay, find the length of the arc BCD to 2 decimal places. Okay, that's easy. It's r times theta is the length of the arc. I know what the r value is because it's the radius of this sector, which is 3.5. And I times it by the angle that it subtends, which is 1.77. So all I need to do is 1.77 times 3.5. 77 times 3.5. That is to 2 decimal places, 6.20. Is it meters? Yes, meters to 2 decimal places. The answer in your calculator gives 6.195, but that rounds to 6.2. Okay, find the area of the sector FBCD. Okay, that's also easy. Area of a sector is half r squared theta, so that is going to mean it's a half of 3.5 squared times by theta, which is 1.77. And I want that to 2 decimal places, so 0.5 times by 3.5 squared times by 1.77 to 2 decimal places, that's 10.84 meters squared. So again, that's nice and easy. And then find the total area of the cross section of the tent to 2 decimal places. Well, I've got this green sector bit now. If you think about it, I've got all this. So really, all I have to do now is add on the area of these 2 triangles. I think I can do that because the total area is going to be 10.84. Well, I tell you what, we won't round. Rounding, what we'll do is we'll keep, so the 10.84, let's get rid of this. The 10.84 came from a half of 3.5 squared times by 1.77. So that's the bit we know, plus we need 2 lots of the triangles. And the triangles are half times A, well we know one side, which is 3.5, times by another side, which we know is 3.7, times by sine of, and now we need that angle. So let's be very precise here. If this is 90 degrees, that's pi over 2. And I need to take away, by symmetry, 1.77 over 2. Because this straight line from F to C is going to split that 177 in half. So I've got 90 degrees minus a half of 1.77. So actually, this is going to be pi minus 1.77 over 2 in there. And that's nice because the 2 and that half will cancel. And now I can just plug this into my calculator and get the results to 2 decimal places. So 0.5, well, it's just going to be the answer, my calculator, plus brackets 3.5 times 3.7 times sine of fraction, shift pi minus 1.77 all over 2, close brackets, done. And apparently, to 2 decimal places, I got this as 19.04 meters squared. Right, so how can I tell that my answer makes rough sense? Well, imagine I create a rectangle, like so it just bounds the tent, like that. That is terrible. What is the height of this rectangle? Well, it's 3.5. And what's the base of this rectangle? It's 3.7 times 2, which I believe is 7.4. Is that right? 3.5 plus 3.5 is 7. Yes. So if I do 7.4 times by 3.5, that's 25.9. So I know my answer has to be lower than 25.9 because the tent is clearly smaller than that rectangle. 19.04 seems legit. I've done all my calculations properly. So yeah, I'll take it. That seems legit to me. Okay, another geometric problem. If you want to pause the video and give it a go yourself. Okay, the figure below was constructed as follows. ABCD is a square with side length of 8 and 4 identical quarter circles whose centres are located at each of the 4 corners of the square are drawn inside the square. The radii of the quarter circles are such that the 4 quarter circles meet at the centre of the square. Show that the area of the shaded region is that. Right, so what is this trying to say? If I draw a line from AC like that, or C to A, as I did it, then the radius is clearly half of the diagonal of the big square. That's important. So if I had an 8 by 8 triangle like this, this thing here is going to be 8 root 2 by Pythagoras. 8 squared plus 8 squared is 128. 128 square rooted is 8 root 2. Therefore, the radius of each of these quarter circles is half of 8 root 2, which is 4 root 2. So that's pretty straightforward. Next up, what I'm going to do is I'm going to assume the following. Imagine I draw a line from A to the centre like that, which I know is 4 root 2. And I'm just going to consider this sector here. Now this is really easy. If I draw a line from the centre down like that, then do you agree that this can be broken into two bits, i.e. there is a nice triangle here, and then I am left with this orange section here. Why is that useful? Because of those orange sections, do you agree I've got 8 of them? Yeah, let's count them. I've got 1 here, 2 there, there's 3, 4 here, there's 5, 6 there, there's 7, 8 there. So if I can just find one of those bits by symmetry, and all I have to do is multiply it by 8 and I'll get the answer. So what I need to do is find the area of the sector and minus subtract the area of the triangle. Is that possible? Well, yes, because I know the hypotenuse here is 4 root 2, and I know that this length here is 4 because it's half of the square. Next up, I know what this angle here is because it's 45 degrees. Now pi over 2 is 90 degrees, so this angle must be pi over 4. Now I'm ready. The area of the sector, which is a half r squared theta, minus the triangle, which I think I can just get away with. It's just half base times height. But we can do it as half of a times b times sine of the angle. So let's deal with it. The sector. So it's a half of 4 root 2 squared times by the angle, which is pi over 4, minus, and then for the triangle it's going to be half of one side, which is 4, times by the other side, which is 4 root 2, times by sine of the angle, which is pi over 4. Okay, let's deal. 4 root 2 squared, I believe that's 32. 4 squared is 16. Root 2 squared is 2. 16 times 2 is 32. 32 halved is 16. Divided by 4, this becomes a 4 pi. The half and the 4 cancel to make a 2. Sine of 45 degrees, or sine pi over 4, is actually root 2 over 2. So that 2 and that 2 will cancel. So it looks like I'm left with 4 root 2 times root 2, which is 4 times 2, which is 8. Oh, that looks nice. So I've actually got 8 lots of 4 pi minus 8. Okay, because this was one of those crazy loopy things. Now 4 pi minus 8 is the same as 4 pi, or 4 lots of pi minus 2. So if I've got 8 lots of this thing, 4 times 8, that means I've got 32 lots of pi minus 2. And there you go. That was it. So yeah, really nice question. Got you thinking about breaking down shapes into simpler ones and then scaling them up, and a bit of symmetry there. So yeah, good question. Okay, now this question was taken from an advanced extension paper. It's quite difficult. We're going to have to use differentiation here. You're going to have to differentiate intuitively as well. So if you want to pause it and give it a go. I'm going to go through it in a second. Okay, so figure 1 shows an equilateral triangle LMN of side 2 centimetres. The point P lies on LM such that L to P is X, and the point Q lies on LN such that L to Q is Y. The points P and Q are chosen so that the area of LPQ is half the area of LMN. Right, so what that's saying is this little triangle here this little triangle there, has an area half of the big one. Okay, show that x times y is 2. Okay, first of all, this is an equilateral triangle, so that angle is easy to find out. That is just going to be 60 degrees, but in radians, that's pi over 3. Yeah, because if pi is 180 degrees, then I just divide it by 3 to get 60. The more you use radians and you're more fluent with them, you'll just spot that, nice multiples of pi pop out. Okay, so what we're saying is that where is it? LPQ, that area, so triangle LPQ is half the triangle LMN. So half of the triangle LMN, well, that's a half of one side, which was 2, times by another side, which was 2, times by sine of pi over 3. And LPQ is going to be a half of one side, which is x, times by another side, which is y, times by sine of pi over 3 as well. Now this is nice because we can get rid of these brackets. Whoops. Now look what happens. Half and 2 cancel, half and 2 cancel. You can divide by sine pi over 3 both sides, so actually what you've got is a half xy just equals to 1. And if half xy equals to 1, you can times both sides by 2 to get x times y equals 2, and that's fairly straightforward. Okay, part B, find the shortest possible length of P to Q justifying your answer. So what we want is to minimize P to Q for a particular value of x and y. So there's two ways we could have gone about it. We could have minimized PQ with respect to x and set it equal to 0, or we could minimize PQ with respect to y and set it equals to 0. So first of all, let's try and find an equation for PQ. And thinking about it really carefully, I think the only way to go is if we've got one side, another side, and the angle, and we're trying to find the other, then I think we're going to have to use the cosine rule. That is p squared equals one side squared plus another side squared minus 2 lots of one side times the other side times by cosine of the angle in between, which is pi over 3. Now cosine of pi over 3 is actually 1/2. So that half and that 2 will cancel. And then look, we know what x times y is. That's just 2. So we've actually got pq squared is x squared plus y squared minus 2. Now that's great, because if we try and find dpq by dx, for example, we're going to make y the subject, so y equals 2 over x. So that means y squared is 4 over x squared, which is the same as 4 lots of x to the minus 2. So actually, pq squared is x squared plus 4x to the minus 2 minus 2. Now, here's the tricky bit. You could square root all this thing and then differentiate it. But in order to do that, you'd have to use the chain rule. The really sneaky thing here is, because, and this takes a lot of insight, because PQ has to be positive, and it clearly does, you can't have a negative length, then that means the minimum PQ must be the minimum for PQ squared as well. Think about it. Okay, so if we just differentiate this quantity PQ squared with respect to x, x squared becomes 2x, 4x to the minus 2 becomes minus 8x to the minus 3, and the negative 2 becomes 0. If we set this equal to 0, then we'll get 2x equals 8 over x cubed, because that's what x to the minus 3 is. If we times by x to the 3 both sides and divide by 2, we get x to the 4 equals 8 over 2, which is 4. We square root both sides, x squared equals plus or minus the square root of 4, which is 2. Plus or minus square root again, we'll get x equals. Now, we're dealing with real things, so we won't worry about the minus 2. If we square root 2, we'll get plus or minus root 2. And again, x has to be a positive value, so you won't bother about the root 2. Now, x equaling root 2 will work. How can I show that it's the shortest possible length? Well, I'm going to need to find the second derivative of dpq squared by dx, and 2x will become 2, and minus 8x to the minus 3 will become plus 3 times 8 is 24, x to the minus 4. If I substitute a real value in there, it's going to be a positive, which means we're dealing with a minimum. So we're minimizing the length PQ here. Now, x equals root 2 will give a minimum value of PQ. And now I can substitute that back into here and see what we get. So PQ squared will equal x squared, which will be a 2, plus 4 over x squared, which will be a 2, minus 2. Well, the 2's cancel, 4 over 2 is 2. So now PQ squared is 2, which means PQ is the positive root of 2. So actually the shortest value that PQ can be is root 2. There you go. Okay, mathematicians know that for any closed curve or polygon enclosing a fixed area, the ratio of area enclosed over the perimeter is a maximum when the closed curve is a circle. Okay, by considering 6 copies of triangle LMN suitably arranged, find the length of the shortest line or curve that can be drawn from the point LM to a point on LN to divide the area of triangle in half. Right, now this one, really cool actually. If I've got a triangle looking like this, this is an equilateral triangle, well it's supposed to be, let's do it properly. Something like that. Man, I can't draw for toffee. Right, here's my equilateral triangle. And suppose I want a curve like this that will split the area into 2. So the bit inside the curve is half of the big bit. We're told that this is a maximum when the closed curve is a circle or part of a circle. Well, let's suppose, now the big clue, to be fair, is, by considering 6 copies suitably arranged. And you should know that 6 equilateral triangles can be formed to make a hexagon like that. And I've drawn that terribly. But the point is, if this curve continued to make a circle, then it follows that that circle, because it's a half of each of the individual triangles, that circle should be half the area of the hexagon. So, what is the area of the hexagon? Well, the hexagon is just 6 lots of the triangles. So that's the hexagon. So that's 6 lots of, the triangle will be a half of one side, which is 2, times by another side, which is 2, times by sine of pi over 3. Well, sine of pi over 3, or sine of 60, is root 3 over 2. So the 2 and the halves cancel, that 2 and the half cancels, so I actually got 6 root 3. The circle has to have an area of a half of that, so that means the circle has an area of 3 root 3. So, if I consider the radius of that circle, then pi r squared equals 3 root 3, which means r squared equals 3 root 3 over pi, so r is going to be the square root of 3 root 3 over pi. Now let's look back over here. Well, r in this case would have been x and y. So find the length of the shortest line or curve. Well, we don't want that. We want this bit, the p to q bit. So we now have r is this, and each of these angles are 60 degrees, which is pi over 3. And we know how to find the arc because it's just r times theta. So if r is the square root of 3 root 3 over pi, and theta is pi over 3, which is 60 degrees, the way we're going to do this is pi over 3 is the same as pi squared over 9 square rooted, times that by the root of 3 root 3 times pi. This can be the root of the whole thing times together, which is 3 root 3 over pi times by pi squared over 9. That squared of the pi is going to cancel with that pi. That 9 will become a 3 to get rid of that. So we've actually got the square root of root 3 pi over 3. That's perfectly valid, but then I can divide by root 3 top and bottom so that that can disappear and that can become over root 3 like that. And to be honest, if you've got square roots inside of square roots, then you might as well have irrational denominators. You might as well go YOLO all out. So something like that. And if you're interested what that number is to a couple of decimal places, then shift square root, where are you there? Fraction, shift pi over shift square root 3. This is approximately 1.35 to 2 decimal places. But the exact answer is the square root of pi over the square root of 3. So yeah, this was an Advanced Extension Award question. This is what a Year 13 would have sat 3 or 4 years ago now. It was one of the latter questions. It would have thrown Year 13s up. You can follow it and see what I've done, and you're doing really well. But yeah, that's it. Radians. I've uploaded a load of stuff. Give it a go.